Welcome everyone to our next topic this week, which is going to be charging systems. And the charging systems, we've got some pretty specific objectives here. We want to be able to recall the components of the charging system and what their actual functions is in the system. We need to know the operation of that alternator. Part of that alternator is a voltage regulator. We need to understand its operation and abilities. We need to know the location of where these voltage regulators are on most of our late model vehicles. We're going to discuss the purpose of an alternator vacuum pump, and then we're going to discuss some of the three basic types of charge indicators and their function. We also want to discuss how that charging system supplies the current to the electrical components when the engine's running. We need to understand this relationship between the battery and the components that need this electrical energy that's there and how we maintain that as we drive the vehicle. And we're also going to talk about how it re-energizes the battery on the vehicle. And that process has changed as vehicles have become more focused on fuel efficiency and providing as much horsepower to the drive wheels as possible for the client. When looking at the charging system components, these are pretty common among every vehicle out there. So for example, we would have a battery in every vehicle to help get it started. And then we would have some kind of ignition switch to turn the vehicle on. We need to have an alternator. On most internal combustion engines, we would see an alternator belt of some sort that runs this alternator. We would have a voltage regulator that controls how much voltage or current is actually being pushed out. Some kind of charge indicator to indicate if we are charging or losing charge. And then some kind of harness to connect all of these components together. One important factor to understand is that we're going to be changing mechanical energy into electrical energy. So in other words, some of the power that the engine is creating is being taken to drive this alternator and has to overcome these magnetic fields, which means that alternators indeed rob the car of some horsepower and dependent on the charging needs of that vehicle. The alternator has components that are comprised of the rotor assembly, which is field windings and has claw poles and a rotor shaft that contains slip rings for the rotor. And this is the moving part. It rotates, in other words, the term rotor. Then we have a stator assembly, and these are the windings. There's three of those windings that are part of the stator core, and they contain the output wires. It also contains the brush assembly that has the housing brushes for it that keep the contact with the actual rotor. There's a rectifier assembly that contains diodes and then a heat sink, and then what they call a diode plate with some electrical terminals. In addition, there's a fan and a pulley assembly on the face, and that contains a spacer, a pulley, and a lock washer with a nut that holds it on. And you can actually change those over depending on what your needs are. And then of course we've got the housing, which is the drive-in of the frame with a slip ring and an end frame that has end bolts that contains the whole unit under one assembly. You can see here that the rotor assembly itself is one of the main components of a simple alternator, and it's mounted on this shaft. And that shaft actually has a bunch of windings around it with this strong magnetic field of these north and south poles. This is what's going to induce that voltage into the actual stator. The shaft is mounted on roller or needle bearings in most cases that allows it to spin freely. And it is turned by the alternator belt. The belt, of course, is tied to the actual engine itself. The main part to the rotor assembly is, of course, its partner, the stator assembly. And the rotor goes inside this and spins very close to it. The stator surrounds that rotor, and it serves as the output winding. As those magnetic fields are going past these windings, it induces a voltage. There are two types of windings around the stator. One is known as a delta type stator, and one is known as a Y-type stator, actually spelled W-Y-E. While there are some important differences, the biggest thing to know is that the wire ends from the stator windings on a Y-type stator look much like a Y, and that they produce good current at low engine speeds. The delta type stator, on the other hand, are connected end to end with no neutral junction. Two circuit paths are formed between the diodes during each phase, or AC voltage output from the alternator. Delta type stators are used in high output alternators. The alternator brushes ride on slip rings to make a sliding electrical connection. The slip rings are mounted on the rotor shaft to feed a low current into the rotor windings. Each end of the field winding connects to one end of the slip rings. An external source of electricity is needed to excite the field windings and produce a magnetic field. The small brushes have brush springs that push the brushes out into contact with the slip rings. Since the current into the rotor windings is low, these brushes are small compared to the motor brushes. The next assembly that we need to talk about is the rectifier. This rectifier is designed to change alternating current to direct current, AC to DC. Automobiles run on 12-volt DC current systems. However, we have AC generated by the alternating current. The stator output is sent through diodes, and diodes act as one-way check valves. This allows us to eliminate one half of the AC voltage that would be above and below the 0 point. The diode output is connected to these alternators in order to create this rectified signal. Here's a typical method of the wiring inside the housing for the alternator. You'll notice here that there are the three brushes or field windings that run out around the outside of the rotor assembly, forming this Y style winding. At the back of that housing, you'll notice the diodes that are signified by a line and an arrow. The line and the arrow indicate the direction in which current can flow. In other words, if you look from the bottom up, electricity can flow up through the wire, but can't flow back down through that wire. And that allows us to separate the downside or the below zero side of the AC signal and capture the positive side of that signal. On the front of the alternator, typically you'll find a fan and pulley assembly. The fan is mounted on the rotor shaft, which causes it to spin. It's spun by an alternator belt that connects to the engine. The alternator pulley can come in a variety of forms: a V-belt configuration, a cogged V-belt, or a ribbed belt design. These fans are essential and can be changed, both the pulley and fan, to cause it to spin faster or slower based on RPM, as well as how much air wants to be drafted in through the alternator to help with the cooling. Another very important component of the alternator is the voltage regulator. That controls the alternator output, and it wants to maintain it producing around 13 to 15 volts when it's charging. It must be replaced and not repaired in almost all instances. Often today, on most modern alternators, the voltage regulator comes as an assembly when being replaced. Voltage regulators can come in a number of different variations. On older vehicles, there are external regulators and contact point regulators. Some of the old Ford pickup trucks would actually have this regulator that was external to the alternator. On newer vehicles, the voltage regulator is contained inside the assembly of the alternator housing, and it is an integrated voltage regulator. The voltage regulator operation today is mostly controlled by an integrated circuit to control the alternator regulation. To increase alternator output, an electronic voltage regulator allows more current into the rotor windings. This strengthens that magnetic field around the rotor. More current is then induced into the stator windings and out of the alternator. To reduce alternator output, the electronic regulator places more resistance between the battery and the rotor windings, and field strength drops and less current is induced in the stator winding. Also keep in mind that the alternator RPM can also have an effect on the regulator as it wants to increase the charging output. So this allows us to drop that voltage down and not continually increase it as the engine speeds up. Here we can see the electronic voltage regulator aligned with the alternator. What you'll notice at the top of it is where the battery is, and our terminal A is our sensing voltage wire there, kind of keeping an eye on what the battery voltage is at. And based on what it sees there, the electronic voltage regulator can induce more voltage into the rotor windings through the actual field terminal at the slip rings, right? We'll put more voltage down there. Then based on that, the stator winding can see what the fields are that are coming back, but actually pushes up through the 6-pack of diodes at the top and actually creates that clean DC voltage going back to the battery. We can see a close-up of the diode trio here, and you can see that this basically allows a certain amount of current to go in one direction. So as the stator gets induced current, it cleans up that stator current to feed the stator current to the voltage regulator and rotor on the unit. But it rectifies this current into a single-sided DC voltage for us that can be used by the car. A feature of newer alternators is temperature compensation. Temperature compensation is usually taken care of through the regulator. There is a thermistor inside here that changes output as the outside temperature changes, so that when the output is needed in cold weather, the voltage is actually increased, since there will be more demand from the battery to crank over a cold engine. A warm engine, it can decrease this voltage, and this is actually a good thing. We don't want to be overcharging. Some voltage regulators cycle the rotor field current on and off to control charging system output. This process is called field circuit modulation. For example, if the battery is discharged, the regulator may cycle the field current at 90% of the time to increase output. If the electric load is low, the regulator may cycle the field current off 90% of the time to decrease output. The percentage of time the field current is on controls the alternator output. A capacitor can be used in the alternator to prevent radio noise. It absorbs alternating current inside the AC generator. The capacitor can also protect the rectifying diodes from high voltage spikes and damage. I often like to think about capacitors as electrical shock absorbers, much like the shock absorbers on our vehicles. They are able to absorb the fluctuations in electricity that do occur. In a computer-controlled voltage regulation system, the vehicle's onboard computer regulates the alternator's output, eliminating the need for a conventional voltage regulator. The computer controls the duty cycle of the alternator's field windings. The duty cycle is the amount of time, given as a percentage, that current is fed to the windings. When the electric load is heavy, the duty cycle is long. This causes the alternator to produce a high output. When the electrical load is light, the duty cycle is short and the alternator's output is low. A duty cycle of about 50% is normal in most systems. In some vehicles, alternator output is intentionally increased above the normal charging voltage of 13 to 15 volts. For example, some heated windshield systems require the alternator to produce up to 70 volts to send high current through the windshield heating element. The windshield heating element is a field of conducting material bonded inside the glass. The film is so thin that it is invisible. The conducting material or film is usually a zinc and tin oxide substance bonded between two layers of glass. When the windshield heat is activated, a control module switches the alternator to full field, no regulation, and sends the resulting high voltage output only to the windshield. The remainder of the electrical system must be disconnected from this high voltage to prevent component damage. The other electronic components are therefore disconnected from the alternator and operate on battery voltage. Again, different manufacturers handle this differently. For example, some vehicles would have additional spotlights, for example, on them, and those high voltage bulbs sometimes require high output, and the alternator needs to go to full field. Here is an illustration of what this might look like. You'll notice that the heated windshield has a direct line between the alternator output control relay to the heat windshield control. On here, when the signal is sent to the vehicle, the voltage regulator detects that the heated windshield has been turned on and tells the alternator output to give it full field. This disconnects it from the rest of the normal system in the car, so not to produce over current or voltage for the other systems involved. A quick note to keep in mind is that an alternator output voltage of 30 to 70 volts is enough to cause serious electrical shock and injury. Typically anything over 50 volts is considered high voltage, so we want to use caution when working with these higher voltages. Some vehicles have an alternator vacuum pump. Most commonly, these are diesel engines. Diesels do not use a throttle valve and therefore do not have a source of vacuum. In these cases, a pump is put on the back, a vane style pump of the alternator that generates a vacuum source that can be used for other items on the vehicle that need to be actuated. For example, power brakes, vacuum diaphragms that are located in the vehicle. Alternator shaft spins this additional component as well as the alternator since it rides in the back. Here's a picture of what that might look like. Pretty much it's an alternator, much like what we're used to, just with this additional component located in the back that creates vacuum for systems that are in need of it. The last component we'll discuss is the charge indicator light that's found on a vehicle. And the charge indicator light can be just a simple indicator light that glows if the alternator output voltage is abnormal. Some vehicles have a voltmeter, and that measures the alternator voltage output. And lastly, some vehicles come with what they call an ammeter, and that measures the alternator's current output. These indicators are usually mounted in the dash of the vehicle, and all vehicles have some kind of indicator, or at least came with one from the factory. So keep an eye on this alternator as a diagnostic tool when looking at the charging systems. All right, so lastly, if anyone has any questions, please feel free to reach out to me either via email or perhaps in one of our face-to-face settings. But please don't feel afraid to ask any questions so that I can make anything that is maybe unclear a little clearer for everyone. Thank you and see you next time.